Thank you very much, and well, good evening from me, but I presume that at least for people in India, it's good afternoon and coming into evening. It's a pleasure to be here. As Mani has said, I'm going to talk about stratified turbulence and mixing that results from that. And I'm going to do this in two parts. So today I'm going to talk about some fundamental aspects of stratified turbulence, in particular, as Mani has mentioned, the scaling, relevant scaling for stratified flows in these contexts, and also and some consequences of that. And then tomorrow I'm going to talk more specifically about a particular study that we've been carrying out here in Cambridge, which I hope you'll find interesting. As I said to Mani, I'm happy to answer questions during my talk if you wish. If you put them in the chat, I will try and be aware of them and respond to them, and certainly answer questions at the end. I'm going to focus very much on oceanographic applications just as a context, but of course stratified turbulence occurs in many situations, not geophysically, not just in the ocean, but also in the atmosphere, and of course in many other contexts, in particular in industrial processes, but I'm not really going to talk about those per se. I want to focus on the sort of oceanographic issues. And one of the reasons, of course, is that there's a lot of importance in modeling and understanding the ocean and atmosphere in terms of climate. We want to know how the climate system responds to the changing levels of CO2 in the atmosphere and what's going to happen. And a good part of this is the way the heat that is put into the atmosphere is then put into the oceans, and what that interaction is. And that's really what I'm going to focus on in this couple of lectures. So to start off, I'll just show you a picture of a temperature stratification in, sorry, I'm just trying to get rid of my picture of me somehow. Can't seem to do that. Anyway, okay. This is a picture of the temperature stratification in the Pacific, measured 40 years ago, but obviously still current, showing in colors, and you can perhaps read the temperature contours. So 1 degree, I can't see to make my mouse work. 1 degree on the blue line, and then up to 10 and warmer waters at the surface. And this shows clearly, I think, that there's a strong stratification in temperature from the top to the bottom of the ocean over 4,000 to 5,000 meters. There is a temperature difference of perhaps 20 degrees from top to bottom, maybe slightly more in the tropics. And that stratification, of course, is one of the main features of oceanic structures and circulation. What happens is that the surface waters in the low latitudes near the equator get warmed by the sun, as you can see, and cold water is produced at the poles. You see particularly clearly in this picture the South Pole on the left, bringing cold water which sinks and flows northwards along the bottom of the ocean towards the equator and so on. And of course, there has to be some interaction between the warm water at the surface and the cold water below. Otherwise, the ocean would eventually fill up with very cold water. And that's not what we observe. We observe this stratification. So some of the heat at the surface gets mixed down. And the caption that I've copied from this publication says that the water at the bottom is warm by diffusion. I changed that to mixing, It's the mixing process that causes that, is one of the things that I want to talk about today. And how this looks on a more schematic measure is shown here. This really is, there's data from the Atlantic, but this is just some schematic with the arrows here. So as I said, there's net heating of the ocean surface over lower latitudes, and net cooling at higher latitudes. And this cooling produces flow of cold water down to the bottom of the ocean. And then that has to be mixed with the warm water at the surface, and in order to get the stratification that we see here. And the issue, of course, is, as everybody knows, hot air rises, so does hot water relative to cold water. So the hot water at the surface wants to stay there, and the cold water at the bottom wants to stay at the bottom. And to lift up the cold water from the bottom, you have to do work. And so it's really how that happens that we want to talk about in the context of this lecture. Okay, so here's one example of how this mixing takes place. So this is in the Brazil Basin in the Pacific. And what you see here are measures of the dissipation in this basin. Doesn't really matter, the geography doesn't really matter. But what you can see here is in these colored bands, measures of the diffusivity as measured in this very important experiment and measurement series carried out by Jim Ledwell and published in Nature 20 odd years ago. And you can see that regions of red and yellow colors imply high diffusivity, so high rates of mixing. And so obviously in this case, much of it is concentrated near this rather rough topography that's outlined in black near the bottom. But you can also see relatively high rates of mixing quite high up in the water column as well. And this is one evidence of how this takes place in the ocean. The thing to notice here is that the diffusivity range, on the color scale at the bottom, covers a range up to about 10 to the minus 4 meters squared per second, and 1 times 10 to the minus 4, so the sort of yellow color, is still 10 times the molecular diffusivity of heat in water, which is 10 to the minus 5 meters squared per second. So anything above 0.1 in this picture actually is significantly greater than molecular diffusion. So which is why I said that heat doesn't diffuse down. The rate would be far too slow. It has to do it at a rate which is at least 10 times faster than the molecular rate, and maybe 100 times faster in some circumstances. And so that suggests that there's a turbulent process going on here that creates greater rates of mixing than you would expect just from diffusion. And so we're going to discuss that and how that takes place as we go forward. And here is a picture of the dissipation rate averaged across the global oceans. And it's in rather different units, but the numbers are comparable to what I've just shown you. So many times the molecular value. And you can see here, the main message I want to show you here is that it's very variable, that there are regions where the values are quite high. If, for example, if you look across the Pacific and I don't quite know what, oh, sorry, I don't quite know why I can't get my mouse to work. Anyway, if you look across the Pacific, you can see a high band across the equator. That's associated with the equatorial undercurrent, which flows across the equator. You can see high values of mixing up in the northwest of the Pacific associated with the Coriolis current. And you can see high values in the Atlantic on the right, both across the equator and also up associated with the Gulf Stream off the east coast of the US. And there are other places as well, such as around Africa and so on. So we see across the oceans significant amounts of mixing and quite patchy in places. I think some of the places it's patchy because we don't have much data actually, but you can see quite a bit of variability. And one of the things we want to talk about is kind of how that all works. Okay, and so this is a schematic taken from a paper by Chris Garrett, and this is what I want to talk about really. So one of the major inputs into mixing, there are two really, but one at the surface is the wind. The wind moves the surface and makes the flow turbulent. This generates internal waves basically on the stratification at the bottom of a mix layer, which is near the surface. And these internal waves propagate and they induce horizontal currents, as you can see here. Internal waves are also produced through tidal currents flowing over topography. And that's one of the reasons why in the pictures I showed you before here, there's a lot of activity around this topography because of flow generated by tides at deep down, because this is at 4,000 meters below the surface. And these
so
also
Paul,
generate.
There is a question in the chat box, if it's okay with you.
I'm just having trouble with my mouse for some reason. I don't know why.
Can I just read out the question?
Yeah, could you read it out, please? That would be good.
Yeah, this is from Mukesh. He asks, is there a reason the diffusivity is high across most of the coastline?
Oh, I think that's so we're referring to. Sorry, now I can't do anything.
I think he's referring to the previous slide.
Yeah, around the coast. Yes, I think there is. I think tidal motion creates quite a lot of flow in shallow water, and as a result of that, there's quite a lot of mixing in shallow waters near coastlines. So where the ocean shallows, there is usually quite a lot of mixing, and there was a time when I think it was thought that almost all of the mixing in the ocean took place around the coasts. But now I think we see evidence in other places as well. So I see there are more questions in the chat. Do you want to? I just can't seem to get the chat to come up on my screen. I don't know why. Can you? Is there any more to read out, Manny?
One more question says, what does averaged mean here?
I think it means average over depth and over time. But to be honest, I'm not entirely sure. I think that's what it means. Yeah.
That's it for now, Paul.
Okay, thank you. All right. So what the result of all of this is that there are currents in the ocean which can schematically be represented by this horizontal currents on the left of this picture, and on scales that are of orders of tens or so meters. And this is a typical situation where the flow is in opposite directions and as you go vertically, and that's a shear flow, and that's one of the main things I want to talk about in the course of these lectures. This leads to some instabilities and overturning of the flow, and eventually turbulent mixing, which takes place at very small scales. So we can stir fluids up, but in order to mix irreversibly, that means you change the density of a fluid element irreversibly. You need to have molecular diffusion play a role. And the way that happens is by generating very small scales. And so we're looking in the context of these lectures at motion on the scales of tens of meters down to fractions of a centimeter, essentially. And what are the processes that take place there, and how are they affected by stratification? Okay. So I'm going to show you, first of all, some sorts of instabilities that we see in these flows. The first is the well-known Kelvin-Helmholtz instability. I've got pictures of Kelvin and Helmholtz here. And this first upper panel will show a shear instability. So what you can see in the picture are two layers of fluid looking at the full depth of a tank. It's a long tank and you can't see all of it. And the bottom layer, the dyed dark layer, is dense fluid. It's salt solution. The upper clear fluid is just fresh water. So there's a density difference between these two layers. And in a moment, I'm going to start the video. You'll see the image tilt, and then we'll generate what's a classical Kelvin-Helmholtz instability. The lower picture is very similar. So there are two layers of fluid, the blue dense layer and a yellowish light layer. And then again, the flow is a shear flow. So there's flow to the right at the bottom and flow to the left at the top, which will be similar to what we see in the tilted tank. But you'll see the modes of instability look quite different. And I'm going to explore that and talk about that as we go forward. So I'm going to start the movies. So you can see the tilt. If you just concentrate on the upper panel for the moment, you see the tilt, the flow accelerates and generates this beautiful set of billows, so-called Kelvin-Helmholtz billows. And you see that again repeated. And now if you look in the lower panel, where again you can see the fluid moving in opposite directions, the waves moving in opposite directions, this is speeded up. This flow looks quite different. Doesn't have the big overturnings that you can see that are characteristic of this aspect. And really what we see are just very small little cuspy waves occasionally, quite a different form of instability. So there are different modes of instability in these systems. And the question is, how do they mix? What do they do? And how can we characterize them? The one in the bottom panel is known as a Joubaud instability or Joubaud wave. And here is a picture of Joubaud, a Swedish oceanographer who first did a theoretical study of these waves, linear stability analysis. And I'll talk a little bit more about those later on. But what I want you to take away from this picture really is just the difference in the two structures that you see here. So you can imagine that the effects on the stratification are quite different in the two cases. And so depending on which one of these you think happens, you would expect the answers to be the results of the consequences to be really quite different. Okay. So I'm going to move on. And the same is true in numerical simulations. So this are simulations from Hasham Saliapour from Toronto. What you're going to see here on the left, and well, in both panels, you see a stratified shear flow. These are numerical calculations, and they're initial value problems. So initially, the flow is set up with a velocity difference between the two layers. And what you can see here is a representation of the stratification. So the green is dense and the purple is less dense. And this transition here represents the transition from the green to the purple. So there's a change in density as you go across this region. And the only difference between these two simulations is that the vertical distance over this, in this case, of this transition between the green and the purple is broader than in this case here on the right. Okay, so I'm just going to show you what happens in this case as well, and just bear in mind that these are just two different simulations. So let me see if I can get this to work. Here we go. So that's the one on. So here they go, and now you can see, I hope, quite different behavior. So this big roll up on the right, sorry, on the left, and the subsequent breakdown to turbulence is very similar to what we saw in the top panel of the previous experiment, the Kelvin Helmholtz one. On the right-hand side, I don't know if you noticed, but the initial instability was much smaller, and we don't get this broadening, huge broadening of the interfaces we saw on the other side. And I'll go back and start, and so you can look at the right-hand panel this time. So let's do that. Sorry, here we go. Let's do that. Whoops, sorry. Okay. So I hope it's working. Yep. So now if you focus on the right-hand panel rather than this big roll-up, we see here, as you'll see, a much smaller wave, a little bit of cuspy material, and this is much more like this lower panel of the previous experiment, which was an experiment. And now you can see that the range of mixing is much weaker and much less in this numerical calculation as well. So we see both in the lab, as I showed you in the previous experiment slide, and in numerical simulations, a big difference in what happens. And the only difference here really, and the same is true to some extent in the previous case, is really the structure of the density field. And it makes a huge difference to what the outcome is. So understanding how that works and plays a role is part of what I want to go through in the next couple of lectures. Okay. So I'm going to start off by talking about some fundamentals and some scaling today. And as I said, then get on to a particular study that we've been carrying out on an experimental system, which addresses many of these questions as we go forward. Okay. So a little bit of background. So basically, the density field is a function of space and time. Oops, I don't know why I can't find my mouse. Anyway, so you can see we typically divide up the density field rho, a function of space, a vector x, and time, into three components. One is a constant reference density. The second is a vertical variation density, z is vertical, which really is just a result of the hydrostatic structure. And then a perturbation about those two densities. And in the ocean, the variations in density are caused by salinity and temperature. I've really only talked about temperature, but of course there are variations associated with varying salinity. But in every case, essentially the variations about the reference density are small. So as I've written here, rho bar plus rho prime is small compared to rho zero. And when we write down the equations, we deal with the hydrostatic part, the term rho bar, which is just a function of z, by cancelling it out with the hydrostatic pressure. I won't go into the details. So the thing that we're really concerned with from a dynamical point of view is the perturbation density, and it affects the dynamics through the buoyancy. So we multiply the perturbation density by gravity, g, and divide it by this reference density. So the dimensions of the perturbation buoyancy are the dimensions of gravity. And because rho prime is very small compared to rho zero, these accelerations, the buoyancy is small compared to g. So typically the order of 1,000th of g or 100th of g, that kind of value. So the buoyancy forces in the interior of a stratified fluid, in the ocean, in the atmosphere for that matter, are low compared to gravity itself, probably 100th or 1,000th of gravity in many situations. Okay, so I'm going to first of all talk about, show you what happens with a canonical shear flow. So just imagine that we have a flow in which the density varies, and so the buoyancy varies linearly a constant rate from a value B at the bottom to a higher buoyancy, so stably stratified, highest buoyancy at the top, B plus delta B, and I've written the definition of B on the left hand side here. Just again, it's G, the density minus rho 0 over rho 0, and a shear flow. So the velocity changes with depth, going from a value U at the bottom boundary to U plus delta U at the top. And of course, we can move in a frame of reference where we are only concerned with delta U. So we just move at the speed U. And the fundamental parameter that describes the stability of this system is a Richardson number, and it's denoted here by RI for Richardson with an O for overall, because it represents the gross stability of the whole system. And it's a dimensionless number that you can construct out of the difference in buoyancy, the difference in velocity, and the depth of the flow, H. And if you look at as I said, the dimensions of buoyancy written in blue are the same as gravity, so acceleration, length over time squared. And so the dimensions of the Richardson number, as you can see here, are length, H, acceleration, LT to the minus 2, and then the velocity, LT to the minus 1, all squared. And you can see that those dimensions cancel. And so this is just a number, a dimensionless quantity, giving a measure of the overall stability of the flow. And we'll look at that. Let's suppose that we, in this flow, imagine that we take a dense parcel of fluid and move it from the bottom to the top. So we take this circle or sphere of fluid with initial buoyancy B and move it right to the top. Change in potential energy of that is essentially H times delta B. And the change in kinetic energy, if it reaches the top, is delta U squared. And so this Richardson number represents the ratio of the potential energy to the kinetic energy in that flow, roughly speaking. Not exactly, but close enough. And so really, it's only possible to move this parcel of fluid from the bottom to the top and to acquire the new buoyancy and density if you have enough kinetic energy, so more kinetic energy than you need to lift this fluid up, which means that this Richardson number needs to be less than 1. So essentially, unless that's true, it's impossible to move. You don't have enough energy to move a parcel from bottom to top. So let's look at the ocean. So in the ocean, as I said, the depth of the ocean is 1,000 meters or several thousand meters. So H is of order 10 cubic meters. A typical velocity difference between the lower slow-moving ocean and things near the surface is about a meter a second. And a typical buoyancy difference between the bottom and the top of the ocean, for example, from those pictures I showed you of the temperature, is about 0.01 meters per second squared, that should be. Sorry, meters per second squared. And that gives you a value of the Richardson number of about 10, conservatively. And so that's clearly much bigger than 1. So there's a problem. The question is, well, are there shear instabilities? Because we have seen that we need Richardson numbers less than 1. And so how do shear instabilities that are observed occur? And that's one of the questions I want to address today. And really, the answer is of this form. So, as I said, we start off with this very simplified system of a linear variation between B and B plus delta B and the velocity. We could imagine other systems where the profile is not just a straight line. And in that case, the Richardson number, we can define a Richardson number, which is a function of Z, the height, just being the gradient of the buoyancy with respect to Z divided by the square of the shear du dz squared, and you can check that that's also a dimensionless quantity. And in the case when dB dz is a constant and du dz is a constant, so in this case big delta B over H and big delta U over H as well, you can see that this equals the overall Richardson number in that limit. And so one of the things which in fact was pointed out by Stuart Turner in his very nice book, I hope many of you have read it, or if you haven't, please do, Buoyancy Effects in Fluids, in chapter 10, he says, well, you can always arrange things so that the gradient Richardson number is whatever you want, as small as you like, by transforming these linear gradients into a series of layers and interfaces. So as I've shown in this picture here, you start off with, you make for example, if you look at the buoyancy, you have a region where the buoyancy is constant, a layer, and then a rapid transition across some region, and then another layer, and the intermediate place is an interface. You can do the same with the shear, and then you can always make the gradient Richardson number at every point here as small as you like. Certainly in the case where the buoyancy is constant, the upper interface, that dB dz is 0, so the Richardson number is actually 0 in both the layers, and across the interface you can always make it as small as you like, essentially because you've got the square of the gradient of velocity on the bottom. So the way out of the dilemma of having a large overall Richardson number is to create layers and interfaces, and these then create shear layers. And just as I showed you in the experiments and in the numerics, that's the reason why we study them, because we have a shear here across some interfacial region that causes the mixing, and so it's a fundamental property of these systems, and looking at them is important from that point of view. Okay, so this is what happens. Here's a picture of shear flow instability in the ocean, and so what you're seeing here are actually backscatter images from acoustics, but these red regions represent variations in density, and you can see lots of structure and overturning features in this picture across a distance of a few kilometers. It's caused by the shear flow over this Camarina sill, so we clearly see evidence of instabilities, and so even in systems where we know the ocean as a whole is very stably stratified, we certainly see these instabilities taking place as a result of shear flow action. And I'll just show you one other example. This is an example taken in the Pacific. It's a recent publication, and these are temperature measurements taken over 36 minutes. You can see the time interval at the top. These are three separate intervals. So for example, if you look at panel A at the top, you can see at about 800 seconds a big event where light fluid is brought way down into the again over but again, notice it's only over a meter or so. So these are relatively confined behavior, but they're rare actually. And what we see more often is shown in the second and third panels. The second panel just shows this very sharp interface with small fluctuations about it over a long period. And the one at the bottom shows similar structure, but perhaps for the first first 800 seconds on the left, you see what appears to be small scale mixing. So the upper panel here looks very much like the Kelvin-Helmholtz instability process that we saw in both the numerics and in the in the tilted tank experiment. And the bottom two panels are much more like the Kelvin, the Helmholtz instability that takes place on we saw in the lower panel of the experiments and on the right in the numerics. So there appear to be these two processes happening. How do they interact? How often do they occur? It seems from this and from the work that Alexis Kaminsky describes that actually the big overturning events are much rarer than the persistent small scale mixing that you can see in the bottom two panels. But this is still perhaps a very open question. It probably depends where you are and so forth. But anyway, it gives us a context, I think, in which to study these things. Okay, so I'm going to move on now and just do some scaling analysis. And I don't expect you to follow all the analysis here, but I'm just simply going to give you the mathematics so that you can refer to it later. But these are the standard equations of motion. So we have the momentum equations. The fluid is essentially incompressible. We have diffusion of mass, which we'll write down as diffusion of density, but you can think of temperature and or salinity, where kappa, the coefficient, is the diffusivity. The stress tensor is the usual pressure plus the rate of strain tensor, Sij, given here in terms of velocity components. Okay, so they're the standard equations which we will start with. And we make the Boussinesq approximation, as I said, which is that the perturbation densities are small compared to the reference density, but we retain the buoyancy term. So we retain the term involving gravity. So the equations then become, the momentum equation becomes the UDT plus U dot grad U on the left, the perturbation pressure, because we've cancelled out the hydrostatic pressure, the buoyancy term associated with the perturbation buoyancy, and dissipation through viscosity. And similarly for the density, we now write in terms of perturbation buoyancy. So it becomes this equation. W here is the vertical velocity, and N squared is the buoyancy frequency. It's given here in this box and is related, of course, to the vertical gradient of density. And so essentially, when you move up and down with a vertical velocity W in a background density gradient described by N, you generate buoyancy. So if you take that little parcel at the bottom and move it up to the top, the buoyancy is given by that difference. And of course, that tends to push that heavy parcel back down again. So that's what that second equation represents. And we represent the strength of the stratification by the buoyancy frequency. Now, in general, the buoyancy frequency can be a function of all dimensions of space and time. But in these, at least in the mean, in these stratified shear flows, we're really concerned with the vertical variation in density. So N is a function of Z. Okay, so what one should always do in these circumstances, and I'm following here two very excellent papers by Paul Bilan and Jean-Marc Chamaz, and a follow-up paper involving the same authors, where they looked at the scaling for stratified turbulence. So you imagine we have a flow with some velocity scale U and two length scales. We'll imagine that since it's probably the case that it's difficult to move things vertically when the flow is stably stratified, we might imagine that the horizontal scale and the vertical scale of motion is different. And we'll write alpha as the ratio of the vertical scale to the horizontal scale. And we probably expect alpha to be small. So we probably expect things to be much easier to move things a long way horizontally, quite hard to move them vertically. And what represents essentially the strength of the flow compared to the strength of the stratification can be represented through a Froude number. F, which is the ratio of the velocity to the stratification. So UN over a length scale. And we have two length scales, so we have two Froude numbers, a horizontal Froude number FH and a vertical Froude number FV. They're again dimensionless quantities, n times a length. N has dimensions of 1 over time, so the denominator has a velocity scale and cancels out the dimensions of the numerator. So then you can scale the various quantities as you wish. So you scale the horizontal velocity by this scale u. The vertical velocity, it's not obvious why you should scale it like this, but you scale it like this, as we'll see. So in terms of u, the horizontal Froude number squared over this quantity alpha. The horizontal velocity scales by LH, the vertical scales by LV, the buoyancy by u squared over LV. So again, dimensions of acceleration, L t to the -2, and the pressure in the usual way, rho naught u squared. And if you do that, you can write down the equations with these new scales. So I've separated them out now into the horizontal components of velocity UH, the vertical equation with W, continuity, again, I've separated out the third equation down with the horizontal velocities and the vertical, and the fourth equation is the buoyancy equation, and I've taken the prime off B, so this represents the perturbation buoyancy and P represents the perturbation pressure. So this is a simple scaling argument, and you simply go through this process and using those scales that I gave you, this is what you get out. And the terms that come out of here are, I've kept it all in terms of the horizontal Froude number, this aspect ratio of the two scales alpha. And we've got two new parameters that have come in. One is the Reynolds number, which is, of course, the ratio of the inertial forces to the viscous forces, defined at the bottom here. And again, I've used the horizontal scale for the Reynolds number. And Prandtl number, which occurs in the last equation, which is the ratio of the viscosity, kinematic viscosity, and diffusivity of the density field or buoyancy. So these are the two other parameters that come out of this scaling analysis. And of course, what we choose to do now depends on taking various limits of these equations and so forth. So let's, and I hope that's all clear. As I said, the vertical velocity is Z, X and Y are the two horizontal directions. Yes, and there it all is. Okay. So now we're going to look at the strongly stratified limit. So we're going to take the case where the Froude number is small, tends to 0, so that the stratification is strong, N is large, NLH is large compared to the flow, but the Reynolds number is high, so we expect turbulence. So RE U LH over nu is large compared to 1. And the ratio of these two, the Reynolds number times the Froude number squared, is also large. And you can see that if you look at the first equation, for example, you're going to get a ratio of the, if I was to divide through by the Froude number squared, I'd have a term on the right-hand side, which involves the Reynolds number and the Froude number squared, and that term will be large. So 1 over that term will be small. Okay, so the first thing is to say that because we think, so I'll just go back here one step, because alpha, this term in the brackets in the first equation is small, we expect this first term to be more important than the horizontal variations, and so we can neglect that. And if we take this limit, we're then going to cross out a number of terms here, and so this is where we end up with our set of equations in that limit. Okay, so the main reduction is in in the vertical equation, where are we? Sorry, this one. So if we look at the second equation down, you can see that we've got the Froude number squared on the left. I should have made it red, sorry, which multiplies all of the inertial terms here. And because the Froude number is very small, all of the terms on the left-hand side disappear, as do the terms on the right. And when you get to the vertical equation, the second equation down here, you're just left with essentially a hydrostatic relationship between the perturbation pressure and the buoyancy. As I said, we can then cross out these other terms because of this limit of large product of the Reynolds number times the Froude number squared. And this quantity, that product is known as the buoyancy Reynolds number, REB. So it's an important parameter, and we'll see this come into play quite a lot later on in my talk. So in this limit, then we're able to remove the two terms on the right-hand side, and then we can now do one further step, which is to say that we expect alpha, the ratio of the scales, to be comparable with the Froude number. I'm sorry, that should be little h on f. And that means that we can eliminate the further terms that I've crossed out here. Okay, so what you see then is in essentially an uncoupling between the vertical and horizontal scales. So there's no vertical velocity left in the first equation because that term cancels out. So the horizontal motion is independent of the vertical motion. The vertical equation corresponds to just hydrostatic variations between buoyancy and pressure. Then we have continuity, the third equation, which is just, again, to do with the horizontal velocities. And then we get a buoyancy equation, which again relates the changes in buoyancy essentially to the vertical velocity. So you're moving up and down against the stratification, and N has disappeared because it's incorporated in the buoyancy. And these equations are very interesting because they're self-similar. So if I describe, take a constant quantity gamma and rescale the buoyancy frequency by gamma, the vertical velocity by gamma, the vertical scale by gamma, the vertical velocity W, U3 by gamma, and the buoyancy by gamma, then these equations don't change. And you can check that for yourselves. I hope it's obvious, but I think it's obvious. And you can just rescale them. So that has important consequences. So that means that, for example, as you increase N, because of this scaling, and this is the Z component, as N increases, then you expect the vertical scale of the motion to decrease, which is very, it's what you expect. As you make the flow more stratified, you expect the vertical motions to be inhibited, make it more difficult to move vertically. And what this says is that because they scale like this, that the vertical scale is proportional to 1 over the buoyancy frequency. And so to make it dimensional, we've got to make this into a dimensions of a length. The only other parameter we have at our disposal is the velocity. And so that means that you expect the vertical scale to scale, like U over N. So, as I said, one of the things of trying to get away from this situation where you start off with a uniform gradient of density and velocity at very high Richardson number, and you can't do the transformations, you don't have the energy to move the parcels up and down, the way to break that is to break up the system into a series of layers. So this is an experiment that we carried out here a long time ago now by Joanne Holford, who was a student of mine. We took a uniform stratification. So if you look at the graph on the right, panel, you can see that the initial stratification, its density plotted on the x-axis and height on the vertical axis. You can see initially that it's uniform, and over time, this develops into a series of layers separated by sharp interfaces, as you can see here. As time progresses, we move to the right of those pictures. And what we were doing in this experiment was simply dragging a grid. You can see if you look at the picture on the left, there was a grid of vertical bars, and we just dragged them back and forth through the fluid. You can see the turbulence generated in the wake of this grid. And out of that turbulence came this ordered structure of layers and interfaces. So this is the way this fluid gets around this problem, this energetic problem of having a large overall Richardson number and creates small Richardson numbers, because in the layers there's no stratification, and it's just all concentrated at these interfaces. And that's the way that does it. And if you measure the depth of these layers compared to this scale U over N, these are the experimental results, and you can see that they fit quite well a line which is about 3 times U over N. So let's try and explore why that might be the case. So I'm going to go back to these equations and look at, so we're now looking again at the case where the fluid number is small, the ratio of scales is small, and we're just going to look at linear two-dimensional internal waves. So we're going to cross out the two nonlinear terms in the horizontal momentum equation, the second term, and in the buoyancy equation, the second term, the third equation down. And we end up with a set of linear equations. We're going to suppose that the velocity v in the y direction is 0, just for simplicity, and then write down solutions for the velocity, horizontal velocity u, the vertical velocity w, the buoyancy b, and the pressure p as a set of waves e to the I kx plus mz minus omega t. And if you substitute that expression into those 4 equations and look for a non-trivial solution, you get the usual dispersion relation, which tells you that the frequency omega of these waves equals k squared, the horizontal wave number, divided by m squared, the vertical wave number, times n squared. Okay, so I'm trying to think why I want to say k is much less than m. Oh, yes, okay. So, all right, so I'm not sure it does imply k is much less than m. The point is that if the scales are large compared with the vertical scales, then k is much less than m, and the frequency of these waves is then much less than the buoyancy frequency n. So I think my implies is back to front there. But the interesting thing is, if we go back to this experiment, we were dragging this bar back and forth at a speed u. So this speed u is given, and you can ask what waves stay in phase with this bar. Well, they're the waves that travel with the same speed as u. So the wave speed at the bottom here, c, is omega over k, and that in the x direction. And from this equation above the dispersion relation, that's just n over m, and that's equal to u, if the waves are traveling at the same speed as the bar. And that means that the vertical wave number m is n over u. And so these are waves with a wave number n over u, so a vertical wavelength of 2 pi u over n. So that means that each half of the wave is just 3, or pi n over m. So what you expect is a vertical scale which is pi u over n, and it's very close to the value that we measured there of 3. So again, what we're expecting to see here is a close interaction between turbulence and internal waves. This causes this change in the stratification. That change in the stratification allows the Richardson number to be relatively small everywhere and for mixing to take place. And so it generates the mixing that we're interested in this context. Okay, so I've nearly finished. I just want to say one other thing, I think, and that is just to look again at this buoyancy Reynolds number. So one of the things that that we are interested in is the turbulent dissipation in a system, and if the flow is not stratified, then the turbulence dissipation takes place at small scales, but it's fed by energy at large scales, and these scales. So just on dimensional grounds, if you have a flow with speed u and a length scale LH, the dissipation scales like u cubed over LH. So the buoyancy Reynolds number, REB, as I said, it's the product of the Reynolds number and the Froude number squared, is u cubed, when I write them all out, nu over n squared LH. And so if I now take out the u cubed over LH as epsilon, the viscous dissipation, then I write the buoyancy Reynolds number in terms of epsilon, the dissipation, over nu n squared. So that's a very useful way of thinking about it. So this buoyancy Reynolds number, this fundamental parameter that you need to be large in order to have stratified turbulence, can be thought of as the ratio between the turbulent dissipation and nu times the background stratification, measured through n squared. Another length that comes out of this process, called the Osmodov scale, is given by the square root of the dissipation epsilon over n cubed. And this is a fundamental length scale, which we think is generally regarded as the smallest scale at which buoyancy starts to no longer play a role in the system. So large scales obviously are strongly affected by stratification. If I move things a long way and I'm taking heavy fluid and moving it a long way up, I have to do a lot of work. And so stratification is important. If I take something and just move it a tiny bit, then that tiny bit, not much stratification, doesn't really matter. So where is that transition? And that is usually regarded as the Osmodov scale, given here by epsilon over n cubed. I'm sure you'll be familiar with the Kolmogorov scale, which is the scale at which dissipation takes place through viscous effects, written here as L eta, which again from dimensional arguments comes out to be the viscosity cubed over the dissipation all to the quarter. And so we can write the buoyancy Reynolds number as the ratio of the Osmodov scale to the viscous dissipation scale to the 4/3. So the condition that you want stratification, you want stratified turbulence to be vigorous, the Reynolds number being large compared to 1, tells you that there's the big ratio between the Osmodov scale and the dissipation scale. So what we're imagining is big scales are strongly affected by turbulence until you get to the Osmodov scale, and then it doesn't really matter. And then it takes a while before you have to go smaller and smaller scales before dissipation takes place. And that separation is important for vigorous turbulence in these systems. So we'll come back and talk about the buoyancy Reynolds number, but what I want you to think about is a region in spectral space, essentially between scales that are affected by stratification above the Osmodov scale, and below that, it's really, they don't matter anymore, and it's really moving down to just viscous effects. Okay, so I think that conveniently brings me to the end of what I wanted to say today. I'm just going to give you a preview of what we're going to talk about tomorrow, just for a minute or two, just so you know what we're going to do. So I'm going to talk about this experiment called the stratified inclined duct. So it is an experiment where we set up a stratified shear flow. So we have a reservoir on the left, which has dense fluid, a reservoir on the right, which has less dense fluid. As you can see, the density difference is delta rho. And we tilt this long tube slightly at a small angle theta to the horizontal. And the dense fluid runs downhill to the right. The light fluid runs uphill to the left. Excuse me. And as a consequence, we set up a stratified shear flow. So difference in density between the clear fluid and the dyed fluid, and a difference in velocity. And by changing the density difference and the tilt angle, we can change the conditions at which this turbulence occurs. And so what I'm going to do tomorrow is explore what we observe in this system, and talk about, in particular, the energy, how the energy that starts off as potential energy here, because we've got a difference in density, drives this flow, creates kinetic energy, and how that creates mixing. And so and I'll talk about that at my tomorrow. So thank you very much.
Yeah, thanks a lot, Paul, for that very interesting talk. There is one question that appears. There are a couple of questions that appear on the chat box already. Would you like me to read them?
Yeah, I can't seem to get my mouse to work at all.
Okay, so I will read them, no problem. The first question is by Devang, who asks, during the development of Kelvin Helmholtz billows in shear instabilities, the density interfaces overturn and the local n square becomes negative. That is unstable stratification. How is the buoyancy Reynolds number defined there?
Well, it's not defined then in that sense. So, I mean, it's a good question, because actually this is one of the issues, as you rightly point out, during these processes, the stratification changes, and that changes n, and that makes a difference, obviously. There are two ways of dealing with this. One, of course, is to look at some average buoyancy frequency, which over time, for example, in that context. So the time when it's negative plays a relatively small role compared to the other times. The other way of doing it is to resort the density field so that it's always stable. I mean, it's possible to do that. It's so-called Thorpe scaling, Thorpe sorting, where you move the density field around, and then even though local areas are unstable, you can resort it to a stable background. So you can still make a useful definition, even though I agree at instance in time, the stratification is not characterized necessarily by that.
So the next question is from Tanmay Agrawal. How can we characterize buoyancy frequency in cases where we observe a horizontal stratification? Example, lock exchange configuration, displacement, ventilation, etc.
Well, yeah, I mean, I think it's not always appropriate just to use n. That's right. I mean, in a lock exchange, which, I mean, this picture that I have up now, for example, if there was no tube here and there was just a vertical barrier and we were to remove it, then the stratification is really determined by this difference delta rho. And what you see in terms of n depends on how the flow develops, I think. So I think one wouldn't characterize it in terms of some gradient in that particular case. You'd use the initial density difference, I think.
The next question comes from Jitendra Raju. How long in time will the density interfaces, how long can they sustain in the ocean? Will the horizontal gradients in density surrounding the interface regions, will they be important?
Yeah, I think they can be sustained for a long time. I think, I mean, there is evidence that they can be sustained for many sort of, what would I call it, advective time units. So times over which turbulent processes act, they can be sustained for long times. Of course, it's obviously very difficult to measure interfaces in the ocean because they do move, they're advected around, and when when you're measuring things, you tend to be in one place. So it is hard to do that. I mean, and there are clear evidence. I mean, in certain circumstances of double diffusive interfaces which last for months. It's not so clear to me that that's true in other circumstances, but yeah, I think they're a relatively persistent feature, actually. Yeah.
Are there other questions from the audience? There are no more questions in the chat box right now.
Okay.
We have plenty of time for questions.
Yeah.
So if there are other questions, please feel free to put them in the chat box or unmute and ask your questions.
I have one, if I may.
Yeah, please, Philippe.
Hi, Paul. Thank you very much for your talk. It was very, very nice. You mentioned that in order for stratified turbulence to take place, there is a need for having enough space in the scale, in scales between the Kolmogorov scale and the Osmidov scale. So what is the physical origin of that reason? I mean, is there the physical significance of the need of this space between these two scales?
Sorry, Philippe, you broke up in the middle. I didn't catch the main part of your question.
Okay,
so I heard about enough space, and then I stopped.
You said that in order for stratified turbulence to take place, there is a need to have enough space in scale between the Kolmogorov scale and the Osmidov scale. So what is the physical meaning of that? Well,
that's a good question. I think perhaps I would put the question I'd put my answer the other way around. I think if the buoyancy Reynolds number is not large, in other words, there isn't a significant separation of scales between the Osmidov scale and the viscous dissipation scale, then it seems that dissipation takes place in circumstances where the stratification is still playing a large role. And therefore, there's very little evidence of strong overturning in those situations. So it's more, the flow is viscously dominated at scales which are large, still large, and where stratification is playing a role. So I think you just don't have the energy in the system to drive a really strong turbulent flow in that context. Right.
Okay, makes sense. Thanks.
Does that make sense? I hope it makes sense. Yeah.
So I had a question on the experiment you showed where you said you were dragging a grid in a stratified fluid in your lab experiment.
Yep.
And you showed the stratification where there were layers with strong stratification at the interfaces. So where in the experiment is this, and where is this going? Or when in the experiment? When in the experiment? After how long is that the state that you have shown, and where is it going in the longer term?
Okay, so it takes several hours, and so it's a relatively slow process. What happens, I think, is that over time, the internal waves are generated that are in phase with the forcing, so they move at the same speed as the bars, and they organize through the shear associated with the long internal waves. They organize the flow into these layers separated by interfaces, and that takes a long time in terms of you've got lots of stirring to do to get it organized. I don't really know how that time scales, to be honest. What happens in the long term is that eventually everything gets mixed. So basically, you start off with a series of layers, and perhaps if I can show you, I'll show you. You actually see some of them disappearing. Let me try and show you that again. Yeah. So if you look at, for some reason I can't get rid of me. Oh, here we go. That's better. If you look at the pic, so if you look here, for example, you've got 1, 2, 3, 4, 5 layers. This one's so you can see this one is disappearing. So these two are disappearing into one. And so eventually you end up with 2 layers with a single interface. And then eventually, after a long time, everything gets mixed completely. So you end up with a stratification, which is just the average of the initial stratification in the long term. The time scale for this is something I don't really understand, actually, to be honest. I just know it takes a long time to do it. Okay.
Thank you. We still have time for questions. Are there any? Okay, and Paul, I've also told the participants that they could mail in their questions if they think of something, and you could take them up in the session tomorrow.
Yep, absolutely. Yes. Do they have my email, or should I put it in the chat?
No, I think they can send the email to the email address of the program, and we could just collect all the questions for you and send them to you.
Okay.
Yeah, there's one person who wants to ask a question. Can you please unmute me? Kavyashree, is it possible to unmute or allow Narsingh Jat to unmute himself?
Yes, sir. Yes, sir. Okay. Now participant can unmute themselves.
Thank you.
Hi, Paul.
Welcome,
Very
sir.
nice talk.
Hi, Narsingh. How are you?
I'm fine. Very good.
Good.
Paul, you showed KH billows from some real scale experiments in the ocean, right? From that Nature paper. They had some KH billows. Am I audible?
Yeah. Yes. I just don't understand what you said. Sorry. Say it again.
Yeah. So you showed some real experiments from ocean where you showed KH billows.
Yeah.
And have they worked on what is the criteria based on which it's decided that they will have KH billows or not? Because you also said that they are very rare.
Yeah, I think. I mean, I showed you a picture, didn't I? And I think it's really just a question of how do you interpret that? And I think that's a fairly large scale motion. I mean, I agree that the data is pretty sparse, to be honest. So it's hard to tell. I agree. We don't have the diagnostics you could run in an experiment or in a numerical simulation. I mean, there is the famous video, or no, not video, photos by John Woods taken in the Mediterranean, where he actually photographed a KH billow when he was scuba diving, put some fluorescent in the water, and it was very clear, and you could see a billow, and that was pretty clear. But of course, he didn't have any measurements of anything. So other than, you see a Kelvin Helmholtz billow, and I guess there's a shear flow and stratification, but we don't know what it is. But it's definitely like that.
But then there will be very strong turbulence also, right? Means how does that turbulence affect the KH instability? Is there some studies on that?
Not as far as I know. No, it's a good question. Yeah, I mean, yes, I mean, we tend to look at it in very idealized conditions, I agree, and we don't know precisely what happens if there's background turbulence and so on.
Yeah, what will happen to below size, strength once we vary the different turbulence level?
Yeah.
And how the energy interaction between two would take place, like KH. How the interaction of energy would take place from turbulence to this KH instability?
Yes. Yeah, I think we don't know. I think we don't know very much about these things in situations. I mean, for example, we don't really know what happens in time varying shear flows, for example. So you might imagine, you've got a Kelvin, you've got an internal wave generating a shear flow that's not steady.
Yeah.
And what happens to KH in that circumstance, or in fact any instability, or the Hombo mode. I think that's an interesting area which we don't know much about. And again, so you have to kind of rely on the idea that the time scale for the instability is short compared to some other time scale, and therefore it's okay. But that may not be the case in some circumstances.
So what are the typical scale separation between them, these internal waves and Hombo waves?
Well, Hombo waves are I mean, they're not real. I don't know how to say. Well, I'm not sure there is a scale separation. I mean, when we think about oceanic internal waves, at least when I think about it, which may not be right, I think about something that's relatively low frequency and persists for a long time, and that generates a shear. And on that shear, you can get various forms of instability that take place much quicker, right? And that's so it's I'm imagining that the internal wave field sets up these relatively sustained shear flows for a long period. There are many other contexts where I think it's perhaps easier to see that. So, for example, saltwater intrusions into estuaries is another good example of stratified shear flow, where when the tide is coming in, salt water intrudes into the estuary, and you've got outflowing fresh water, and that lasts for a whole tidal period, basically, or half a tidal period. And then I think you can think about it in those terms. Yeah.
Thank you, Paul.
Sure, nothing.
Are there any other questions? If not, yeah, I would like to thank Paul once again for this very interesting lecture, and we will have a follow-up, as Paul said, at the same time tomorrow.